Okay, so this is a lecture in which we introduce reaction-diffusion systems. Okay, so we are going to see a few things about the diffusion equation, stationary solutions, and other things that are mentioned here. All right, let's start. Okay, so in the first part of this course, we have seen a differential equation describing, in most of the cases, the time evolution of some chemical concentrations, right? Concentration of the species like C1 and C2 up to N, and these variables are non-negative. Okay, they denote the concentration of some chemical species, and we assume that they only depend on time. And the evolution is described by this set of coupled non-linear typically differential equations, which are described by some functions f1, f2, and so on and so on. Okay, so this is the system that we have studied in this first part of this course are homogeneous, and they do not, so the concentration does not depend on space. The assumption is that the system is well mixed, so that reaction times are sufficiently slow such that the system is homogenized at all times. A better description of the system of chemical system reacting is the following differential equations, that now if we want also to take into account the fact that actually this concentration may be dependent also on space and not only on time, we have to extend these equations. So far we have seen this reaction part, and now we add another component, which is the diffusion. Okay, so this term, this coefficient, this is the Laplacian operator. This is operator of second derivatives in space, acting on Ci, the concentration of I, which depends now also on the space x and t. And Fi are the same terms that we have seen before, but now we don't have only one constant value, but we have a Ci that depends also on space. C1, C2, and Cn, they all depend on space and time. Okay, so this is called a reaction-diffusion equation, and here this is the diffusion term, and this is the reaction term. Okay, so combining these two ingredients, we get quite interesting physical phenomena that we see in the next lectures. All right, so in this lecture we forget about this reaction part. Okay, so we start first discussing some properties of the diffusion equation. All right, so the diffusion equation in one dimension, so this first example is one dimension, is described by this simple term. So the Laplacian now is just the derivative with respect of x, second derivative with respect of x. The coefficient here in front is the diffusion, what is called the diffusion constant. Okay, so this diffusion equation in this form can be obtained, sorry for the typo here, from random walks theory. So there is a microscopic theory that one can use to get to this equation. But we are not going to discuss this, how from random walks you can, from Brownian motion you can get this macroscopic diffusion equation. Okay, so let's take this for as given. Okay, so this diffusion equation, it's a continuity equation, in the sense that this can be written as a continuity equation that we know in physics. So it's the derivative of this quantity, this concentration, is equal to minus the gradient, the first derivative of some current. So from this form of the diffusion equation, I see that the current, what is called the current, is just given by minus d, the derivative of the concentration with respect of x. So by taking an extra derivative, I reconstruct the diffusion equation. So this J is what I call the current density. Okay, why is it called the current density? So we see it in the next slide. Okay, so let's consider, for instance, the integral of the concentration. So we have one-dimensional system. We integrate this concentration in an interval AB. Okay, and this integral gives the number of particles that are in that interval AB at the time t. Okay, so we are interested in differentiating this, so we are asking how this quantity changes in time. So, okay, the number of particles in AB. So we take the total derivative, this d dt, I can bring it inside the integral and becomes a partial derivative in t. But now this is exactly the left-hand side of the diffusion equation. So I can replace this in this form, this continuity equation. So it's minus the gradient dx, integrating in dx. This is just the function j, the current at the boundary A, minus the current at the boundary t. So what we see here is that the number of particles here in AB, it's a quantity that can change in time, but it can only change it through flow of the current at the boundary. Okay, either there is current flowing out of the boundary or flowing in from the boundary, okay, into the system, and this is the way. So that there is a conservation. The bulk, the number of particles is conserved. It's only a boundary effect. So if I take in particular the limit to minus infinity, from minus infinity to plus infinity of this, if my process is defined in the whole infinite space, this current goes to 0 at infinity at the bound. So the total number of particles is conserved. So the continuity equation expresses the conservation law, as we know from other example of electrodynamics, for instance, or fluid mechanics and so on. All right, but this formulation in current helps us also understand how a given concentration profile evolves. So I have, say that I have my concentration at x time t at a given time t, and the shape is of this form. Okay, as a function of x here is plotted. Right, so we know the definition of current. Okay, so I can calculate the current anywhere. It's just a minus the derivative. So the current here, particularly the derivative, is negative here of the concentration. Okay, so the current is positive, right? So there is a flow of particle in time, that current that drives me the concentration to so the number of particles to move into this this way. On here, on this side, the derivative is positive, but the minus sign brings a current which is negative. So we see that by plotting this concentration, what this current tells us is that this profile will be smoothened in the course of time. Okay, so it's important to understand this concept of current, and where does it come from. So we have to think that there is that we can derive this this differential equation, this diffusion equation, from the random walk theory. So the fact, for instance, that there is a negative derivative here, it tells me that on the left side of this point there is a bit more random walks than on this point. Okay, so there are more particles at this point than to the point that it's right. Okay, so therefore there will be more particles spreading from this point. The particles spread symmetrically from this point. The particles spread symmetrically from this point. These are unbiased random walk, but because there are more on here on this side, okay, there is a net effect that is shifting the particles here to move at this point, to move to the right. Okay, that's what the story of the current tells us. Okay, so this is the diffusion equation, and for this simple 1D diffusion equation, there is a very simple solution. Okay, that I describe here in the last line of this slide, is that given some initial condition, which is a delta function, so I picked a function at time t equal to 0. Said the concentration is delta function like, so I put at time t equal to 0 all the particles, all the n particles at the point x naught. Okay, this is my initial condition. The solution of the diffusion equation is of this form. At a later time t, this assumes the shapes of a Gaussian. The Gaussian is centered around x naught, and it has a variance this Gaussian, which I read it from here, which is equal to 2 times d times t. This is the variance of this Gaussian, and this Gaussian grows in time. So it's so this variance grows linearly in time. So this Gaussian, it becomes more and more spread. So we see this in the next slide. This is our elementary solution for every point x naught, every initial condition which is delta peaked at time t equal to 0. At later time t larger than 0, we have this Gaussian spreading, and even at a later time this Gaussian becomes broader and broader. But if you go back, and you can verify that in the previous equation, and that if I integrate this from minus infinity to plus infinity, independent on the time, I always get n. This is the total number of particles in my system. So this diffusion process that describes particles that are moving in this infinite line, okay, in this one-dimensional space, but particles do not escape from my system. They always there at later time, and okay, so it's I will find them somewhere. Okay, so this is the underlying conservation law, and that's related to the continuity equation that we discussed in the previous slide. Okay, so now having this particular solution, the solution that I expressed in the previous slide, means that I can solve in practice this diffusion equation, right? It's sufficient to write the initial condition, right? So this is the diffusion equation is an equation, differential equation that I want to solve once given the initial condition. It's first order in time, so if I know the concentration as a function of x at time t equal to 0, I want to solve it and to predict what is the concentration at later time. Okay, so I give you here an example. An example is that the initial condition is a square, is a rectangle of this type. So in between minus an interval minus a divided by 2 and a divided by 2, okay, I assume that initially at time t equal to 0, the particles are equally distributed in this interval. So their concentration is n divided by a if x is in absolute value is smaller than a over 2, or is larger or is equal to 0 if x is larger than a over 2. Okay, so the concentration is 0 outside this interval, it's constant in the interval, and yeah, again 0 also on the other side. Okay, so now it's simple to show that this function that I write here with 3 conditions can be actually written as in a simple form as an integral from minus a divided by 2 to a divided by 2 of a delta function times n divided by a, and the delta function is a delta of x minus y dy. Okay, so it's very easy to see how this works. So let's take an x that is outside of this interval, so either it's smaller than minus a over 2 or is larger than a over 2. Okay, if x is outside of this interval, okay, and if I integrate the y inside this integral, it never happens that this delta function within this interval, that the argument of the delta function goes to 0. So this is precisely, I get 0 whenever x is outside the interval, I get 0. But when x is somewhere inside the interval, by integrating over dy, this delta function fires, and I get n over a. So this is precisely another way of writing exactly the thing that you see here. Okay, but now it's a very convenient way of writing, because I know that given this initial condition, my delta function, so that what happens if I has this as initial condition of my diffusion equation, I know the solution, what the solution would look like at later time. It's a Gaussian that we have already discussed in the previous example. All right, so this is a linear combination of delta functions as initial conditions. So because my my diffusion equation is linear, the solution is a linear combination of this Gaussian, precisely with the same form as it here. So if I have, this is definitely a solution of the diffusion equation, because these Gaussians are solutions of the diffusion equation. And if I go back in time to time t equal to 0, I reproduce exactly the desired initial condition. So this is also another way of writing the same things using what is called error function, okay? And the typical profile, but we could have anticipated also, right? It's of this kind, and you know, and it's a combination of these two error function. And in the as the time goes on, this becomes smaller here, and the concentrations and spreads more and more. Okay, that's also you know, one can plot this. Okay, so one way of solving, therefore, the diffusion equation is try to write this initial condition as a combination of delta functions. Okay, as shown here. All right. Another class of solutions that are also interesting are those that are called stationary solutions. So I'm looking at solutions now where the concentration is depending on x, right? But independent on t. This would happen, for instance, at very long time. So if I let the, you know, I start from an initial concentration and I let the system evolve in time, it eventually reaches a concentration that is independent on time, depending on the boundary conditions and so on. Okay, so now we consider here the one-dimensional case. So the diffusion equation is second derivative of c with respect of x is equal to 0, right? Because dc dt I assume is 0. I'm looking for stationary solution. So in one dimension, the solution of this differential equation is very simple. It's a straight line, right? Second derivative is equal to 0. And this gives a simple straight line. So for instance, I may be interested in, so for instance, a given interval, minus a over 2 and a over 2, and I want to fix the concentration. So at the point minus a over 2, my concentration is c minus, that has certain value here, I call it c minus, these boundary conditions, and I call c plus the other point here at a over 2. And I'm asking, so what is the stationary, given these boundary conditions, what is the stationary solution of the diffusion equation? So it's a line, and just now I have to find the coefficients b1 and b2. This is a simple exercise, and it's given by this form. You see that this form is precisely such that you know, whenever x is, for instance, if x is equal to a over 2, this is 1/2 plus 1/2 is 1, then I get c plus, and this is 0. Okay, so this is exactly the straight line that connects these two boundary conditions. So I can calculate from here the current. I remember the definition of the current, okay, is minus the derivative of this. So you see that this derivative is taken from, you know, this derivative is very simple, and it's given by d, which multiplies the difference of concentrations at the boundaries divided by a. This current does not depend on x, so there is a constant flow of particles here. Okay, so it's the concentration at the boundary is fixed, and the concentration at the boundary, the other boundary, is also fixed. Okay, so particles can come out from this reservoir concentration, flow down here, and they do that at a constant with a constant current. Okay. Okay. So even if the concentration does not depend on time, particles are moving. There is a flow of particle. Whenever there is a gradient in your profile, there is a current. This is a condition of constant current, time independent, space independent. Okay, but it's non-zero. All right. Okay. This is one class. This is a very simple one-dimensional stationary solution. Now I have here another example. This is in 3D. So the equivalent of this equal to 0 in 3D is the Laplacians, okay, the set of second derivative with respect of x, with respect of y, and with respect of z equal to 0, okay. All right, so I have to solve this, but in particular, I'm interested in spherically symmetric solutions, okay. So it's more convenient to rewrite this in polar coordinates. And I want to consider cases where this concentration depends only on the polar distance r, okay, and not on theta and phi, okay. So this Laplacian, okay, in polar coordinates gets only derivative with respect of r, not with respect of phi, not with neither with theta, okay. I assume that this, I want to spherically symmetric solution. So this is my equation, okay, equal to 0, and it's easy to show, okay, this 1 over r squared doesn't do anything, so to have this equal to 0, it must be, well, to have this equal to 0, it must be that what is inside here, it's a constant, and the solution is of this form, is a plus b divided by r, okay, so it changes with respect to 1d, I have 1 divided by r here, and yeah, perhaps is not surprising here. This is the same problem that we have in, for instance, in electrostatic. Okay, the electric potential phi satisfy these equations in a region where there are no charges. Okay, and here you recognize the electrostatic potential that comes from a charge placed at the origin plus a constant. Okay, so this is the solution. This is spherically symmetric solution that we are interested in. And the other thing is that, well, what is the current now? The current is a vector, and it's the gradient of this is equivalent of this quantity in 3 dimensions. So it's a gradient. So I have to calculate the current. I have to you know, take derivative with respect of x, y, and z. Okay, but I'm interested in I have only the r dependence, so there is a radial current. So this vector actually is radially has only a radial component. Okay, and this radial component, you know, I can write this again, this gradient in terms of polar coordinates, and the radial component is just given by ddr. Okay, so this is simple. If I have these initial conditions, and this A and B will depend on the type of concentrations, on how I fix the concentration at some boundary, we'll see it later. But given this form, okay, then my current is just D times B divided by R squared, where B is the coefficient of 1 over R. Okay, all right. Okay, so now we see a specific example of this spherically symmetric solution. So the example that I want to study, again, this is a stationary solution case, is the following. I consider a system, a sphere centered in the origin of radius capital R, and I want that to solve the diffusion equations with the following boundary conditions. The concentration at the surface of this sphere is equal to 0, whereas the concentration at infinity, spherically symmetric, very far at infinite distance, is equal to C. Okay, so you imagine your concentration very far from the origin is it's converging to this value C, and the concentration should drop, right, by approaching this sphere, and should be 0 exactly at the sphere. Okay, and it's very easy. Now we fixed the 2 parameters, capital capital A and capital B, of the previous slide, and the solution is very simple, is of this form. Okay, so you can see this is a 1 over R term, this is the constant. Okay, and you see that this, when small r goes to infinity, is just you getting C, right? When small r equals to capital R, the concentration is 0. So this is the right stationary solution of this diffusion problem with the boundary conditions that I discussed here. Okay, so if you have the analogy of this with electrostatic, what would be the problem of electrostatic? We would have here a sphere, a conducting sphere, with zero potential, and the potential having a finite fixed value at infinity. Okay, this is exactly the same problem in the language of electrostatic. Okay, now if I calculate the radial current, and the only component I have the radial current is given by the derivative with respect of r, so it gives 1 over r squared here, and the current is radially distributed. It goes as 1 over r squared, and it's pointing, so it's negative. It means that that it points inwards, okay, as expected. The particles are, there is a reservoir of particles at infinity at some concentration. The concentration particles flow into the system, and they are absorbed here at this boundary. So you can imagine that this is a kind of sink where the particles are absorbed and are entering in this sink. Okay, and they disappear from my system. Okay, and so there is this radial current flowing in, and importantly, the radial current is going as 1 over r squared. So if I have a point very far away, the current density J of r is smaller, but it becomes larger and larger when I approach the sphere. Okay, so I may also want to calculate the current through a spherical shell. So I take, for instance, a coordinate here, somewhere here in this region, at the distance r, and I integrate over the whole the surface of the sphere, which is 4 pi r squared, okay, times the current density. This is the total current through that spherical shell. Okay. And then you see that by having this r squared here, and I define this current as positive, okay, so I take the absolute value of this, I have 1 over r squared, so the combination of the two gives me 4 pi d times r times c. Importantly, this current is independent on small r, so if I take a spherical shell here, very far away or closer to my boundary, I get the same result. Okay, so this is also expected, right? I have the stationary flow of particles, so if I integrate, okay, over the whole sphere, then a constant density so a constant current. This is the current through the spherical shell. Okay, so an application of this result is that of diffusion limited reaction, and we are discussing here. So we are discussing the following situation. Okay, so we have particles of type A and particles of type B, and they diffuse. Okay, they encounter each other, and as soon as they touch, we assume that they react. Okay, and they react, for instance, forming a complex AB, right? And they are permanently attached, or once they react, they can also disintegrate and goes to zero. But let's assume that they form a complex CAB as soon as they touch. Okay, so this reaction is described by some constant K, right? Which multiplies CA and CB. Okay, let's assume that they react at their first encounter. Okay, so this is a diffusion limited reactions, and I want to know what is the rate KAB. Okay, all right, so I can use this result, and actually this result already tells me what this rate is. Okay, so first of all, I'm considering the following case. I'm considering a frame. So I have two diffusing particles, one with diffusion coefficient dA and the other one with diffusion coefficient dB. So, but it can be shown, I'm not showing it here, that if I take the frame where particles say A is fixed, okay, then my diffusion equation with two species is equivalent to the diffusion equation with only one species, right? Which then diffuses with the coefficient which is the sum of the two diffusion coefficients, B, dA plus dB. Okay, so this is the result. Okay, so actually, therefore, the rate is just given by the, it's relatively simple to show. It's given by this this total current, okay, but instead of having d of one species, I have the sum of the two, okay. And you see that this will react as soon as they touch, okay, and they touch when the particle B is at a distance, if I take the particle A fixed at the origin, is at the distance RA plus RB, okay. So in other words, the result here for KAB is just given by, in this diffusion limited reaction, is given by 4 pi dA plus dB instead of this, and the distance RA plus RB. Okay, so this is the rate for a diffusion limited reaction. So it's the fastest possible rate that happens. Normally, two particles to react, they typically do not react and at their first encounter, but we can imagine that they need to collide with certain velocities and energies such that the reaction takes place. Okay, so this is an idealized limiting case that, you know, considers the case that this reaction occurs instantaneously as soon as they touch for the first time. Okay, so normally we would expect that chemical reactions will not have such a high rate, but typically should be smaller than this, right? If you assume that there is even a small contact, I mean, there need to be some energies or some collision velocities for the reaction to take place. Okay, so this can be seen as the limiting value that for a diffusion limited reaction. So this is describing the fastest possible rate. Okay, and it's useful because it gives us like an upper limit. We normally do not expect to see a chemical reaction with a rate that exceeds this KAB that we calculate here. Okay, so this KAB is therefore, this is given by this, this is a result due to Smolkowski. Okay, we can estimate these for typical values, for instance, diffusion coefficients of, say, molecule in water. Small molecules are the order of 10 to the minus 5 centimeters squared divided by seconds, and assume that these molecules have a radius of roughly 1 nanometer. Okay, so now you combine these two numbers and you get this this KAB, and normally okay, so if you just put this unit together, you see that is length cubed that you get divided by seconds. Okay, but if you multiply this this length cube, which is cubic meter, by the Avogadro's number, okay, this is the number of molecules in a mole of solvent. You can transform this unit and express it in normally a more useful chemical unit used in chemistry is molar. Okay, so molar is the number of moles per liter. Okay, so the result of this calculation is 10 to the 9 of the order of 10 to the 9 mole to the minus 1 molar to the minus 1 second to the minus 1. Okay, so we continue our discussion of diffusion equation, and we discuss a peculiar type of diffusion where the diffusion coefficient here is concentration dependent. And we take a simple example where the diffusion coefficient now depends on C, on the concentration itself, in the following very simple linear way. Okay, what do we have in mind when we take this type of model? So when the concentration is small here, C going to 0, also the diffusion coefficient goes to 0. And at high concentration, C, the diffusion coefficient is large. And this mimics an effect of, we can think about a repulsion between particles, right? So when somehow when the concentration is high, there is a large number of particles in a specific spot. Okay, this particle wants to disperse fast. Okay, then the diffusion coefficient goes higher up. But when this concentration is small and it's going to zero, then the diffusion is also, the diffusion coefficient, and so this particle, they don't move, they don't spread as efficiently. Okay, now it's very simple. We have this diffusion coefficient. We construct the current as usual. We take the gradient of the concentration times the diffusion coefficient, right? We have this type then of diffusion equation. Is still a continuity equation. We built up that way, right? So it describes dispersion of particles not following the ordinary diffusion equation with this term, this concentration dependent term. C naught is a scale of concentrations. We define it in this way, right, to have a quantity d naught, that is the dimension, the units of diffusion coefficients, right? And C naught is also as the unit of concentration, right? This type of equation is obtained by taking the divergence of the minus the divergence of the current here, of the current density, and constructing a diffusion coefficient. So it's of course it's non-linear, so there is a term in C and dc dx. Okay, so it looks a complex diffusion equation, but actually it can be solved exactly in this case, and the solution is shown here. Okay, right, we start again with the delta function as initial condition, and we find that the solution has the following form. So there is a coefficient, a quantity with a unit of length. It has the same dimension as x. This is b, and b depends on time, such that, okay, so my concentration is non-zero only in the region where x, absolute values of x, is smaller or equal than b. And here it assumes a parabolic shape. So you see that it's when x is equal to 0, this coefficient is 1. And when x is equal to b, this parabola goes to 0 at the two sides. It's plotted here. Okay, and this b depends on time. And the solution is also such that the concentration is 0 for x is larger than b. Okay, this b, we said it's depend on time, and the solution yields the following form. The b of t depends on the number of particles, d naught, c naught. Okay, the diffusion. So these two parameters, and more importantly is t to the power 1/3. Okay, so this is a concentration profile that has a sharp front. It's not like the ordinary diffusion where this is spreads like a Gaussian. This front is really going to 0 at this point, and is 0 here further. And this front is moving. This is b of t. It's moving with this power t to the power 1/3. If you want to know the front velocity, we take the time derivative of this one, and it's going to as a power 2 to the minus 2/3. So when time is so this front is moving very fast initially at short times, but this velocity goes to 0 as the time moves on. Okay, so how do we understand this front? Okay, so when the particles are all concentrated close to the origin, that's a delta function as initial condition. Okay, the concentration is very high. The diffusion coefficient is also very large, therefore, because it depends linearly on the concentration. Okay, so the particle want to spread very, very fast here initially. Okay, but as the front moves, this total number of particles is still a continuity equation, right? So the total number of particles is conserved. Okay, the concentration gets lower and lower, and this front moves therefore more slowly, right? With this power law, it's a very peculiar type of diffusion, and it has been used, this kind of diffusion equation with this type of concentration dependent diffusion, for instance, in population dynamics, like dispersion of population. So if if you have a certain population in a certain region, you can imagine that okay, when there are too many members, if the population is very large in a specific region, then it wants the population wants to spread much more than when when the population reaches a low concentration, then it's happy to stay where it is much more. That's why the diffusion coefficient in this model it's concentration dependent in this way. Okay, but this is a kind of phenomenological equations, right? We put this diffusion coefficient with this dependence and we solve the equation that way. We cannot really derive this equation from first principle. Okay, so perhaps it's also important to note here that that in this this B of t also depends on the number of particles, right? In ordinary diffusion, the number of particles is just a prefactor that it's in front of everything, but here it's also inside in this the way this front moves, showing that actually it's characteristic of a nonlinear system, right? So this is a peculiarity again. This front is really going to zero. And we understand why this front is going to zero. Actually, the particles that are here on the top of the front, their concentration is zero, and they are immobile, right? So that they do not spread. Okay, so this is a peculiar type of diffusion, right? Okay, we are ready now to discuss a real reaction diffusion system. Now we have the diffusive part of the reaction part. The system we are discussing here as a first example is a very simple one. Note this differential equation is linear, and this describes a particle that are disintegrating with a certain rate alpha. Okay, that's what you see here. This is a familiar term when we studied homogeneous system, spatially independent system. Okay, so now we have on top of that we have the diffusion equation. So in particular here in this problem, what we are interested in solving this reaction diffusion equation for a stationary profile in the domain X non-negative, right? And we impose a boundary condition to our system, namely that the concentration in x equal to 0 is equal to c naught. Okay, and the stationary profile means that we are not interested in time dependence, but only we are looking at the time independent solution, right? So we set this left hand side equal to 0, and we solve just this simple linear equation, which is second derivative of c with respect of x, is equal to alpha divided by d times c of x. The solution is very simple, is a decaying exponential. There are two solutions actually. There is the exponentially decaying and this exponentially growing solution, but this exponentially exploding solution we disregard as non-physical, so we have only this solution. And the boundary condition is that this initial point x equal to 0 is equal to c naught. Okay, that's what we find here. So we have a characteristic here, length xi, which is just given by the square root of d divided by alpha, right? Okay, it's a very simple. So how do we understand here? So we have particles here are being pumped. If there would be no decay, no alpha equal to 0, then at sufficiently long time this would fill, so the particles would keep coming from the reservoir here to the left, okay, and they would come into the system and would fill it completely. Okay, but because of this decay, now minus alpha of c, the particles are coming in from this side constantly. Okay, and but they are they decay due to this reaction, so they do not reach they reach finite length here, so they explore finite length and then they decay. So this is a stationary profile, so this exponential decay function. Okay, so which kind of system of realization of this kind of model we're thinking of. This is a model for a morphogen. What is a morphogen? So we are here drawing a simple one-dimensional system of cells, okay, which are initially all identical, right? So when an organism grows from a few cells, okay, from one and doubles and three, initially the very first few cycles of divisions, all the cells are identical, right? And then at a certain point there is differentiation. This differentiation often arises typically from the presence of a chemical, right? A chemical that enters the system, say on this side, right? And this chemical is called a morphogen. This morphogen has the property of being able to transform the cell into a specific state. And typically, if this morphogen has a concentration higher than a certain threshold value, C star, say, okay, then what can happen is that the cells exposed to this high concentration of morphogen, they turn into one specific cell. Here in this drawing is indicated by this cross. If the morphogen is lower than this C star here in this side, the cells that have different fate, and they transform into this other type of cell. So when the morphogen can activate the cells depending on its the value of its concentration, can determine different cell fates. Okay, this is how different tissues develop in a multicellular organism. Okay, so this is a very, very simple one-dimensional reaction diffusion model of this type of process. Okay, so this is a model. So you see that here at this point it's a boundary. So all the cells that are on the right and side of this boundary, they are exposed to higher morphogen. And the cells that are here on the here on the left hand side, they are on the high morphogen, and on the right hand side they are at the low morphogen. So they have a different fate. Okay. The problem of this system, of this model, that in a biological system these levels, like on morphogen concentrations here at the boundary, they are not very well controlled, and it's subject to fluctuations. Okay, because of several reasons. This concentration may change, right? In some cells, cells it's higher, in some it's a bit lower. Okay, and this, because we are dealing with a linear differential equation, this boundary condition, actually this C naught, if it's modified and it becomes a bit larger or a bit smaller, then it influences the profile of concentration through all the domain up to x to infinity, right? And now it's very simple, but a small variation of C naught, it produces a small a difference in the position of this domain. Here, sorry, I forgot to indicate what is L. L is the position of this boundary, determining the region at high morphogen, splitting the region of high morphogen to the region of low morphogen. Okay, and this L, that is this position, therefore varies. Okay, so if I increase this C naught a little bit, this L is pushed to the right. Okay, and how much? This is the equation that determines. It's very simple. It's obtained from this equation, right? Okay, so the problem with this model is that if you have fluctuations on input here, then you have they propagate all over the profile, right, at all x. Okay, right. So now we see in the next slide another example of a very, very similar system. Again, there is an example of a reaction diffusion model, but now we have a nonlinear differential equations, and what we are thinking now is of a system where the degradation of this morphogen, this particle x, does not occur spontaneously, like x going to to 0, okay, but the degradation occurs when two of these combine, okay, and they give rise to when they combine, there is some degradation rate, okay. There is, therefore, now the reaction part now it's not alpha times c, but it's alpha times c squared because of this, okay. Now we can ask the same type of question and ask what is the stationary profile. I impose now a boundary condition, c is equal to c naught here at position x is equal to 0, and ask what is the profile of the stationary part. So I have to take this part of the equation set that equal to 0 and solve it, okay, with this initial condition. And the solution is now not an exponential, it's a power law, and it's given by this form, okay. So c naught is the concentration when x is equal to 0, and there is another parameters entering here that is x naught, that is given by this relation, okay. And in particular now we notice that okay, the behavior is quite different, right? You see that x naught depends on c naught itself. So when x is much larger than x naught, this ratio is much larger than 1. Therefore, 1 can be neglected here. And what happens is just that this concentration becomes c naught multiplying by x naught squared divided by x squared. But x naught squared itself contains c naught in the denominator, which cancels this c naught. So it means that at large x, much larger than this x naught, this is a value set by the initial concentration, okay, then this concentration decays, and it's independent on c naught, right? So we have the following situations. We have if we plot this function, it's starting like this, and then it starts decaying at sufficiently large x, like as 1 over x squared. But the important point is that if I have now a variation in input in fluctuations up to a certain from a certain distance on, this variation is not felt anymore by the system. You see that the crucial thing is that this decay does not contain c naught. So a difference in input, if the morphogen is released at varying, fluctuating concentration at the varying concentrations, nonetheless, you know, if our threshold is sufficiently, is not too high in this region, but our C star, say our threshold is somewhere here, it's this threshold point, from this point on, you know, it's quite insensitive to the fluctuations in input of these boundary conditions. Okay, so therefore in this system, different from the linear example shown before, this boundary between the two cell fates, like transforming into a cell with this type of cell or the other type of cell, it's this boundary, this position is much more sharply determined. This is called robust patterning in morphogenesis. Okay, so we need, you know, that's this simple example shows that if our degradation goes via dimers, okay, and not directly spontaneously, then this you know, then this for a morphogen for a morphogen, this type of system gives some robust patterning.